Study Unit 2, Lecture 4. This lecture pretty much carries on where Lecture 3 finished off and will be the final lecture on capacitive components. Plastic film dielectric capacitors are non-polarized, self-healing, and are built by selecting a plastic with a specific dielectric value, which is then coated with a metal layer to form the terminals. As mentioned before, these capacitors consist of a plastic dielectric layer which is coated with a metal layer to form the terminals. The plastic which is selected is chosen for a specific dielectric constant. Different plastics have different dielectric constants, or rather relative dielectric constants, and so a wide range of different capacitors can be manufactured in this way through selection of materials. The construction method used to manufacture these capacitors is called extended metallization, where there are alternating layers of dielectric with metal layers which are interleaved together, and then contacts are created using a process called shooping, where hot solder is sprayed onto the edges of the metallized layers. Shown here are 4 different constructions using this construction technique. The first shows the red and blue lines, which are the metallized layers, with the dotted areas being the dielectric plastic film. The extended metallization term comes from the fact that the metal film which is sprayed onto the plastic connects to the terminals over here. In this example, there are 3 capacitors in parallel to create the overall capacitor. The first 2 metallization layers form a capacitor down here, another here, and another here. This construction technique does not necessarily need to make use of plastic films which have been coated with a metallic layer. This construction can also be used to have dielectric and metallic foils interleaved together to form the capacitive bank. For higher capacities, the dielectric film can be plated on both sides for a double-sided metallized polyester carrier film. This allows for more capacitor regions to be created within the capacitor stack. In this final construction over here, it is a mixed dielectric construction, which means there are multiple dielectric types and possibly foil types within the capacitor stack to create a capacitor with a very specific function in mind. An advantage of such a construction technique using different dielectrics is that a capacitor can be designed which is more resilient to environmental and electrical stresses. For this type of capacitor construction, there is a specification referred to as insulation, which characterizes the ohmic path between the layers and the contacts. This insulation characteristic is something that should be taken into consideration when a capacitor is designed or to be used in a specifically stressful environment. This selection of graphs shown here shows that depending on the type of plastic material or dielectric used, the characteristic of the capacitor can change with things such as ambient temperature, frequency, and relative humidity. For example, depending on the dielectric material used, the capacitance can either have a positive or negative temperature coefficient. The dielectric material can also have an effect on the frequency response of the capacitor. So for some materials here, such as the KSKP and MKP family of plastics, the capacitance will almost not change at all with frequency, but certain materials such as MKN will see a drastic change in capacitance with an increase in frequency. Lastly, again, some materials will show almost no variations with relative humidity, whereas other materials will show quite a large deviation from the design capacitance with a change in relative humidity. There are several electrical characteristics of plastic film dielectric capacitors which need to be considered. As shown earlier, depending on the type of dielectric plastic film used, there is a temperature dependence in these types of capacitor constructions. This can lead up to a variation in capacitance of up to 8% from this graph here. In a similar fashion, there can be a humidity dependence, which can also lead to significant deviations in capacitance. In general, small deviations in temperature and humidity will not permanently affect the capacitance of the device if it is operated within its rated parameters. However, if the device is operated, for example, at very high temperatures for an extended period of time, then temperature cyclic capacitive drift will occur and the capacitance of the device will change irreversibly. Capacitor values can also vary with time, with a deviation of 2 to 3% over a period of 1 year. In the previous lecture, the lecturer mentioned the equivalent series resistance, and this ESR represents several loss mechanisms which are present in the capacitor. These loss mechanisms can be the dielectric loss, ferroelectric hysteresis losses, dielectric conduction losses, interfacial polarization, partial discharge, electromechanical, ohmic losses, sparking, and finally eddy current losses. Dielectric losses are losses which are caused by losses in the actual dielectric material. Ferroelectric hysteresis losses are losses which occur at very high voltages where high field strengths are associated with the high voltage. Dielectric conduction losses are caused by the actual conduction of electrons through the dielectric. Interfacial polarization losses are losses which occur when the electric field changes polarization across the material boundaries which are present in capacitor devices which make use of multiple materials. Partial discharge losses are losses which occur from discharge in materials within the capacitor. This discharge can be caused by using certain liquid materials or gaseous electrolytes, or if the capacitor is damaged. Electromechanical losses are losses due to the piezo effect which cause actual mechanical movement within the structure of the capacitor. Ohmic losses are associated with the ohmic parts of the capacitor, such as the leads or any other conduction paths inside the capacitor structure. Sparking occurs when there is sufficiently high potential across the terminals of the capacitor or parts of the capacitor, and arcs will form between these conducting paths. Eddy current losses are a function of very high electric field strengths and magnetic field strengths. At these high field strengths, the fields will couple into other materials, causing energy losses inside the capacitive device. These factors all combine to determine the equivalent series resistance of the capacitor. Shown in this graph here is the ESR of a capacitor as a function of frequency. The impedance is actually quite high until the capacitor approaches a resonant frequency where the impedance approaches 0. Above this resonant frequency, the ESR will start to increase again with an increase in frequency. Once again, depending on the materials used to build the capacitor, specifically the dielectric material, this ESR Y curve will move around depending on the material types and the operating conditions under which the capacitor is operating. The maximum operating voltage of a capacitor is also a function of things such as frequency and temperature. In this sort of example over here, the maximum operating voltage will start to decrease as the ambient temperature increases past 85 degrees Celsius. The voltage and current dependencies in film capacitors have three distinct regions with frequency. In the first region, the maximum AC voltage which can be applied across a capacitor remains relatively constant, with the air in the capacitor being the limiting factor which regulates discharge. In the second region, the maximum AC voltage starts to decrease as the power limitations of the capacitor come into play. Finally, in the third region, the ability of the contacts of the capacitor to actually transfer the AC energy become the main limiting factor which limits the maximum AC voltage across the capacitor. This voltage behavior for AC signals is only characteristic for sinusoids. For non-sinusoids, there is a different approach to determining what the limitations of the capacitor are. So capacitors which are used for repetitive transient suppressions do not typically have sinusoidal inputs. Sinusoids are relatively easy to work with since they are easy to describe mathematically, but this pulse train over here is non-repetitive and non-sinusoidal, so a different approach is required to see what the maximum power will be which flows through the device when such a pulse train is across the device terminals. Methods include using a graphical design approach to design for this type of pulse train. Another approach is to use the frequency components to see what the highest power harmonic is of this pulse train, and then use that high power harmonic as the maximum power which will be flowing through the device. The remainder of this lecture will have a quick look at DC plastic capacitors and other capacitor types such as EMI suppression capacitors, feed-through devices, ceramic dielectric capacitors, and mica dielectric capacitors. DC plastic capacitors are designed to have a significantly higher capacitance because they are designed for DC only or for very slow transient signals. These devices are typically used in DC link decoupling, and the reason they are used is because they are resistant to voltage reversals in the device, where a typical electrolytic capacitor would explode when the voltage is reversed across the device. A DC plastic capacitor is able to hold and resist this voltage reversal. EMI suppression capacitors are capacitors which are designed to suppress analog RF signals or noise which may be present on lines in the circuit. These EMI suppression capacitors are divided into two classes, Class X and Class Y. Class X capacitors are capacitors which are designed where if the device were to fail, there would not be danger for electric shock or more severe consequences should the capacitor fail. Class Y capacitors are designed for use in applications where should the capacitor fail, there would be a danger to people around it or to the circuit itself. The key difference between the two really is that Class Y capacitors are designed to fail in a certain way in order to prevent further failures in the rest of the system. An example of how the Class Y capacitors are designed differently, they are designed to not short out in case of a failure, where a Class X capacitor may short out during a failure. Feed-through capacitors are used when a conductor needs to move through normally a mechanical barrier and there needs to be suppression of EMI on the conductor. In this sketch here, the feed-through capacitor is a 4-terminal device. It has the input and output of the conductor and then the shielding, which is normally connected to a housing through which the conductor flows. One part of the capacitor is connected to the conductor itself, where the rest of the capacitor is connected to the housing of the feed-through capacitor. This creates a capacitor between the conductor and the external housing of the feed-through capacitor. This is especially useful for when decoupling conductors from the rest of the circuit. Ceramic capacitors are similar to oxide ceramic dielectric capacitors. In ceramic capacitors, the dielectric is formed by baking a non-metal polycrystalline structure to form the dielectric. Ceramic capacitors come in two flavors, high K and low K. Low K devices provide very linear responses with a change in environmental parameters such as temperature and frequency, but offer a low capacitance when compared to high K devices. High K devices are able to achieve a much higher capacitance but sacrifice the linearity which is characteristic of a low K device. Finally, microdielectric capacitors are manufactured when electrodes are plated onto thin sheets of mica. Mica is a chemically resistant clear mineral aluminosilicate which has a plane which cleaves very easily, and sheets as thin as 50 micrometers can be obtained. And that concludes this study unit lecture on capacitors.